Well, there are. For instance, if we take two molecules and force them to go through long, thin pipes, the sort of very small pipes that you get in the pores, as the pores of a piece of unglazed pottery like this, then the faster molecules, after lots of collisions, will find it easier to get through these pores than the slow molecules. And as you remember from the equation, the faster molecules are going to be the lighter molecules. Remember this inverse relationship. Now, you can see that this tube is actually a closed tube. It's closed at this end, so that if I put the bung in here, I seal the air inside the tube. Now, I put the whole thing into the cylinder, like so, and now the pressure of the air inside the tube is being measured through this tube here, back to here. Now, this side is open to the atmosphere, and as the levels are now equal, this side must also be at atmospheric pressure. But what's going to happen if I introduce a gas that's heavier than air? Now, I've got some carbon dioxide in a soda siphon bulb in here. Let me just squirt a little bit in here. Well, that's certainly got nothing to do with increasing the pressure on the outside. The pressure on the outside of the tube is still atmospheric pressure, because what's happened is that the level has risen in this side, showing that the pressure has gone down inside the tube. Is that reasonable? Well, let's have a look at it. You've got air inside, carbon dioxide outside. The air is lighter and therefore finds it easier to diffuse than the carbon dioxide finds it to diffuse in. Therefore, we lose more gas from the inside of the tube, and therefore the pressure inside the tube goes down. Of course, if we were to do it with a gas which is lighter than air, say helium, then we'd expect exactly the opposite effect. Let me try that. I first of all got to empty out all the carbon dioxide. Remember, carbon dioxide is heavier than air. And I'll now invert this because helium's lighter than air, so I've got to trap the helium somehow. I've got some helium in this cylinder here. Let's see if it works. Okay, well, I guess that actually proves the point. But don't go away with the idea that gaseous diffusion is simply a little pretty demonstration like this. We can actually use the principle of gaseous diffusion for all sorts of industrial applications.
One of these occurs in the nuclear fuel industry, where the problem is to separate uranium-235, the isotope used in nuclear reactors, from the slightly heavier but much more abundant uranium-238. Now, the starting point is uranium hexafluoride gas, UF6, which, because it's made from naturally occurring uranium, contains less than 1% of the lighter isotope U-235 that we want. And this is where diffusion comes in. Imagine in the left-hand chamber of the tank that I've got UF6 gas. But this dividing wall is porous, so the gas molecules will diffuse through, and the lighter gas molecules will diffuse slightly faster, so that after a while I'll have a slightly enriched sample in the right-hand chamber. But because the masses are very nearly the same, the speeds of diffusion of the two types of uranium hexafluoride differ by only about 4 parts in 1,000. So just diffusing the gas through one porous wall isn't going to produce a very spectacular effect. But look what happens to this slightly enriched sample in the right-hand chamber. It gets pumped along to another chamber over here, another porous wall, more diffusion, more enrichment. And the gas that didn't diffuse in the left-hand chamber is pumped all the way back to our original tank, and it's recycled through the first porous wall. And this recycling process happens over and over again many, many times through many diffusion stages until nearly half the defined gas contains the lighter uranium atoms, the ones we're after.